Hello everyone, we continue with 5.3 optimization problems involving exponential functions. This is video part 3. So we are going to do another example. Before you watch the rest of the video, you may want to do this question on your own and then check your answers with this video afterwards. So let's read the question. Two different drugs can be used to treat an illness. The concentration in blood of drug A of drug A and drug B are given by Ca of T 1.47 T times e to the power of negative T and Cb of T squared times e to the power of negative T. Calculate the maximum concentration for each drug and the time at which the maximum concentration occur. Like the previous example, to get the maximum concentration, we are going to take the first derivative of those functions, and then we are going to find the zeros of the first derivative. So we are doing part A. Let's start with drug A. So we are going to take the derivative of this function. So 1.47 is the coefficient, so we will keep it as it is. Now we have t times e to the power of negative t. So since there's a multiplication here, when we are taking the derivative, we need to apply the product rule. So derivative of t is 1 times e to the power of negative t plus derivative of e to the power of negative t, e to the power of negative t times derivative of the exponent is negative 1. So that is the derivative of e to the power of negative t, and we need to multiply it by t. So let's organize this a little bit before we factor. So we have e to the power of negative t minus t times e to the power of negative t. So I'm going to factor then. We see that common factor is e to the power of negative t. I'm going to factor e to the power of negative t. Okay, then this gives us 1 minus t. Actually, I would rather to have t minus 1. Therefore, I'm going to also factor the negative sign. So we get t minus 1 here. So again, we are going to make the first derivative equal to 0. We have two factors, e to the power of negative t and t minus 1. Again, this factor will never be 0. And then we can get the 0 from the second factor, t minus 1. And that will give us t equals 1. Okay. Again, to check if this gives us the maximum or not, we can also do first derivative table. So 1, we are going to check the sign of first derivative. And we're going to check increasing, decreasing intervals for Ca of t. So again, time starts from 0. So let's pick a value between 0 and 1. Let's say 0.5. Okay, and check the sign of the first derivative. So we have negative 1.47 e to the power of negative t minus 1. So we have a negative value here, e to the power of negative t. So if you sub 0.5 here, you get e to the power of negative 0.5. You don't even need to use your calculator to calculate that. So 1 over e to the power of 0.5 will be a positive value. Okay, and then if you sub 0.5 here, you get a negative value. So if you multiply all those three, we get positive here. So it looks like first derivative is positive in the first interval. Let's pick another value that is greater than 1. So let's pick 2. So if we do that, again, let me write C prime here. So we are subbing 2. So again, this is a negative value, e to the power of negative t. So that is going to be always positive. And t minus 1. So if you sub 2 here, you will get a positive value. So negative times positive gives you negative value. So then first derivative is negative when t is greater than 1. So based on that, we can see that CA of t, original function, is increasing from 0 to 1 and decreasing when t is greater than 1. So it looks like we have a maximum at t equals 1. So we can also calculate the y value here. Okay, we can take 1 and sub in a CA of t function. So let's do that. So CA of 1, so we substitute 1. So 1.47 times 1 and e to the power of negative 1. Okay, so that gives us 1.47, and this is 1 over e. So times 1 over e. One 0.47 divided by e. So that gives us 0.54. 0.54. That is the maximum concentration. Okay, and that is what the question was asking. Maximum concentration is 0.54. Let's write it. Maximum concentration is 0.54 milligram per liter, and then it occurs at t equals 1 hour. Okay, now we need to do the same process for drug B. So we are going to take the first derivative of CB of t function. Okay, so we have t squared times e to the power of negative t. So we need to again use the product rule to calculate the derivative here. So derivative of t squared 2t times e to the power of negative t plus derivative of e to the power of negative t gives us e to the power of negative t times derivative of the exponent negative 1. And we need to multiply this by t squared. So we have 2t times e to the power of negative t minus t squared times e to the power of, I don't even need to use bracket there, e to the power of negative t. So we can see that t and e to the power of negative t are common factors. So then we get 2 minus t. Again, I want to write it as t minus 2. Therefore, I want to also factor negative sign. So t minus 2. Now we are going to make this equal to 0 and check where the first derivative is equal to 0. So as you see, we have 3 factors in this case. First factor, second factor, and third factor. So the first one, then we get t equals 0. E to the power of negative t is never 0, so we don't get any zeros from there. And from this one, t minus 2, we get t equals 2. So this time we got 2 values as zeros of the first derivative. So let's make the table, first derivative table here. We start from 0, and we need to use 2, and we are checking the sign of first derivative. Okay, so we can pick a value between 0 and 1. Let's pick 0 and 2. Let's pick 1 and sub in here. So if we sub in 1 here, okay, so that is negative, and t is 1, so that is positive. E to the power of negative t is always positive. So t minus 2, if you sub 1, you get negative. So negative times positive times negative gives you a positive value. So let's pick a value that is greater than 2. Let's say 3. Okay. So let me write the first derivative again here. So we are subbing 3. So negative sign. T, we are subbing 3, so that is positive. This is always positive e to the power of negative t. And then if you sub 3 here, you get a positive value. So if you multiply all those signs, you end up with a negative value. So you have negative sign here. Now let's check where the original function is increasing or decreasing. So we have increasing and decreasing here. So looks like we have a maximum point here. So at t equals 0, then we don't have a maximum, because we can't even check where t less than 0. Therefore this t equals 0 is not giving us the maximum value. So maximum is happening at 2. Now we need to calculate the maximum concentration. So we're going to take 2 and sub in CB of t function. CB 2. Okay, so we get 2 squared for e to the power of negative 2. So if we do this, 4 times e to the power of negative 2 gives also us 0.54. 0.54. So maximum concentration for drug B is 0.54 milligram per liter, and it occurs when t equals 2. Okay. Then part B. So we finished answering part A, so let's look at part B. It says if the drugs must be fast acting, which drug should the patient receive? Actually, to answer part B, and actually later on we are going to see that part C as well. So let's sketch the graphs of these two functions on the same grid, and then we can compare which one is fast acting. And as you see, part C is asking if the drug must be active for a long time, which drug should be administered. So if we compare the graph of these two functions, then we can answer those questions. So to sketch the graph, again, I need the inflection points. So I'm going to take the derivative of the first derivative to get the second derivative. So I have, for the first derivative, negative 1.47 e to the power of negative t minus 1. So I'm going to take the second derivative. Okay, so I will keep the constant or coefficient here, 1.47. Okay, now I'm going to apply a product rule here. So derivative of e to the power of negative t, e to the power of negative t times negative 1 times t minus 1, okay, plus derivative of t minus 1 is 1 times e to the power of negative t. And of course, I need to put a bracket here. Okay, so this gives us negative 1.47. If I distribute this first, or you could directly actually take e to the power of negative t as a common factor outside, and that will give us negative 1 times t minus 1, and from the second one we get plus 1. Negative 1.47 e to the power of negative t, so this gives us negative t plus 1 plus 1, so negative t plus 2. So I want to have t having a positive coefficient. So actually I want to factor negative sign. So negative gives you positive. So that will give me then t minus 2 here. So now we should make second derivative equal to 0. So we have again two factors, factor 1, factor 2. By now we learned that e to the power of negative t never become 0. So we can't get any 0 from here. So we can only use this second factor, t minus 2. and that will give us t equals 2. To check if this is really a point of inflection or not, we can do the second derivative table. So 2 second derivative and original. Again, I will start my table from 0. So let's pick a value between 0 and 2. Let's say 1, sub in here. So we have 1.47 e to the power of negative t, t minus 2, and we are subbing 1. So this gives you again, so this is positive. E to the power of negative t is always positive. So sub 1 here, so you get a negative value. Okay, so negative sign. Okay, so positive times negative gives you negative. So looks like we have negative here. So let's pick a value that is greater than 2. So let's say it is 3, okay, and sub in here. So 1.47 is positive. E to the power of anything is positive. Now sub 3 here, you get positive value. So positive times positive gives you positive, okay. So based on that, we can say that original function is concave down from 0 to 2 and concave up when t is greater than 2. So looks like that we have a point of inflection at 2. Okay, so x coordinate is 2. Now we can find the y coordinate by subbing 2 in the original function. The original function is 1.47 t times e to the power of negative t, so sub 2. So we get 1.47 times 2 times e to the power of negative 2. So that will give us 0.397, so almost 0.4. So 0.4. Okay. So 0.4. So that's the point of inflection there. Okay. Again, to sketch this function, we can also look at the limit of them to see their horizontal asymptote. Okay. So let's do it for the first function for drag A. So limit of 1.47 t times e to the power of negative t as t approaches positive infinity. Okay. So t, when you sub infinity for that, you get a very big positive number, and e to the power of negative infinity, right? So you get 1 over e to the power of very big number. So that number is going to be very small number. So you're dividing 1 by a very big positive number. So this is almost 0. So the limit of it is 0. So you're multiplying infinity by 0. So when you multiply any number by 0, you end up with 0. So this limit is 0. So this tells us that horizontal asymptote is y equals 0. So let's check the limit of drag B as well. Limit of t squared e to the power of negative t as t approaches positive infinity. So first one, so we are squaring a very big number. So it is like infinity square. So you get infinity from this. And you have e to the power of negative infinity. So e to the power of negative infinity is like 1 over e to the power of infinity. So you are dividing 1 by a very big number. So again, this is almost 0. So basically, if you look at the limit of it is 0, then you are multiplying infinity by a 0, so you end up with 0. So again, both functions have horizontal asymptote at y equals 0. And again, this should make sense. After you take a drug, after a long time, the concentration of that drug in the bloodstream will be almost 0. So the limit of it is 0. Okay, so we have all the information for drug A. We can sketch the graph of drug A. So we have a maximum point at 1 and 0.54. Somewhere here. And then we have an inflection point at 2 and 0.4. 2 and 0.4 is here. And again, it's because it's a simple graph. I'm not drawing these two first derivative and second derivative tables. I'm just going to use concavity to sketch from 0 to 2. It is concave down. Oh, you can also look at the start point. When t is equal to 0, when you sub 0 here, you get 0. It's actually the same thing with the second equation. If you sub 0 for t, you get 0 for concentration. So both of them start from 0, 0. And again, this should make sense. So, you start taking the drug at t equals 0. And obviously, the concentration must be 0 at that time. So we have a concave down curve up to up to 2, okay, and then it is concave up, and we have a horizontal asymptote at c equals 0. Okay, so this graph is for CA of t. So let's check the second function, drug B. So we already have the first derivative table for the drug B. Now we are going to take the second derivative and find points of inflection. Okay, so we have this, so negative t times e to the power of negative t times t minus 2. But actually, since there is like 3 factors here, taking the derivative from the factored form would be complicated. So we don't want to do that. So we are going to go back and actually use not factored form of first derivative of the CB function. Okay, so we have 2t e to the power of negative t minus t squared e to the power of negative t. So let's take the second derivative from here. So we have t times e to the power of negative t. So we are going to use product rule here. So derivative of t is 1 times e to the power of negative t plus derivative of e to the power of negative t is e to the power of negative t times negative 1, and we need to multiply it by t. So that is the first part. Now we are going to take the derivative of the second term, so t squared times e to the power of negative t. So minus, again, make sure you use brackets here. So derivative of t squared is 2t times e to the power of negative t plus derivative of e to the power of negative t, so e to the power of negative t times negative 1 times t squared. Okay, so I'm just going to distribute these and then try to factor it afterwards. So we have 2 e to the power of negative t, and we have 2 negative 1 negative t, so negative 2t e to the power of negative t. And then let's look at this. So distribute that negative sign. Negative 2t e to the power of negative t. And we have negative t squared multiplied by negative sign, positive t squared e to the power of negative t. Okay, so we see that these two, we can collect these two terms. So we get negative 4t e to the power of negative t plus t squared e to the power of negative t. Now we can see that e to the power of negative t is a common factor. So that gives us 2 minus 4t plus t squared. So we're going to make this equal to 0. And I will need to solve this quadratic expression. Okay. So check if it is factorable. So looks like this is not factorable. Therefore, we are going to use quadratic formula to solve for t. So we get minus b for plus and minus square root of b squared minus 4ac over 2a. So that gives us 4 plus and minus 16 minus 8 is 8. So 2 root 2 over 2. And this gives us 2 plus and minus root 2. Okay. Then we have two t values. One is 2 minus root 2. That is 0.59. And the second one is 2 plus root 2, which is 3.4. 3.4. So this is almost, those are of course approximate values. So this is almost 0.6. So now we can make the second derivative table. So we have 0.6, 3.4, and again we start the t from 0. We are checking the sign of the second derivative for drag B. Okay, so we have 3 intervals in this case. Let's pick a value for each interval and check the sign of the second derivative. So for the first interval, let's pick 0.5. So second derivative, let me write the second derivative function here. So that is e to the power of negative t squared minus 4t plus 2. So we are subbing 0.5. Okay, so you get e to the power of negative 0.5. So that is a positive value. Now sub 0.5 here. Okay, and check what you will get. Okay, so 0.5 squared minus 4 times 0.5 plus 2. So that gives us 0.25, which is a positive value. So this gives us positive value. So positive times positive gives you a positive value. So let's pick a value between 0.6 and 3.4. Let's pick 1. And again, sub in here. So this first part is going to be always positive. So then we need to check actually the sign of this quadratic expression. So if you substitute 1 in here, you get 1 minus 4 plus 2. So that is a negative value. Okay. So let's pick a value that is greater than 3.4. Let's say 4. Again, so e to the power of negative t is always positive. We're only checking the sign of this quadratic expression. Sub 4 there. So you get 16 minus 16 plus 2. That gives us a positive value. So positive times positive gives you positive. Okay. Now we can check the concavity of CB of t. So it gives us concave up, down, up. So it looks like we have 2 points of inflection. Okay. So x coordinates are 0.6 and 3.4. So now we need to calculate the y coordinates of those points. Okay, so we can sub them in a CB function. Actually, if you do that, you will get 0.2 and 0.39 here. Okay. So let's then sketch the graph of drag B. So we have a maximum at 2 and 0.54, 2 and 0.54. Okay, and then we have point of inflections, two of them, 0.6 somewhere here and 0.2. Okay, and other point of inflection is 3.4 and 0.39. So somewhere here. Okay, now again I'm gonna just use the concavity. So we have concave up where t is greater than 0 and less than 0.6. So concave up. Then concave down between 0.6 and 3.4. And then when t is greater than 3.4, we have concave down. Okay, so that graph is for drug B. All right, now let's go back to question and answer those questions. It says if the drug must be fast acting, which drug should the patient receive? Fast acting, we can see that drug A reaches maximum concentration in 1 hour and drug B reaches maximum concentration at 2 hours. So it looks like drug A is fast acting. Okay, so drug A. So let's answer part C. If the drug must be active for a long time, which drug should be administered? So again, let's compare these two. So it looks like drug B is in the bloodstream in higher level, okay, for longer time. Okay, if you compare drug B and drug A, so if we want drug to be active for a long time, so drug B should be picked, should be administered. Okay, so we are done with the second example. Now you can go ahead and look at the textbook questions.